Hello, everybody. Thank you all for tuning in today. We are excited to continue our One Water Perspectives webinar series, and we're continuing today with a presentation from Jayantha Obeysekera, member of the UN Southeast Florida Regional Stakeholder Advisory Committee, and excited he could join us this afternoon. We're still working out the May schedule, and details for our next round of presentations will be announced soon, so look for that email in the coming weeks here. And for anyone who's new to our series, I'm just going to cover a couple housekeeping items. So first, we do record each webinar and post them to our YouTube channel. A link is added to the UN webinar webpage and disseminated once it's available. And second, all the participants have entered this webinar muted, so please enter your questions in the chat queue and we will address them at the end of the presentation. To help facilitate some discussion towards the end, I will also try to turn everyone's mics on who's asking questions so that we can have a little direct discussion with OB this afternoon. And with that, I am excited to introduce our presenter for today. Dr. Obeysekera is the Chief Modeler at the South Florida Water Management District. Prior to his position, he was the Department Director, managing a large group of modelers who conducted regional scale modeling associated with large-scale projects in South Florida. He has served as a member of the Federal Advisory Committee, which directed the development of the National Climate Assessment, NCA, in 2014. He was a lead author for the Southeast chapter of the NCA in 2014. He also served as a member of the Coastal Assessment Regional Scenario Working Group associated with the Department of Defense in the U.S., and he was a co-author of the Regional and Global Sea Level Rise Scenarios for United States, published by NOAA in 2017. He currently serves as an affiliate research professor at Florida Atlantic University. He has served as a member of several committees of the U.S. National Academy of Science covering major water resources projects in Oregon, California, and Texas. And with that, I am going to turn it over to Obi. Take it away.
So I just want to give you a brief history of the water management system in South Florida. Early 1900s, the explorers came to South Florida. They realized this is a unique subtropical climate, and the soil, the organic soil, was a prime opportunity for agriculture and vast extent of flooded land. But they precluded settlement. There's a lot of flooding pretty much all the time. So as the development, particularly starting from the coastal area, progress, there was a pressure at the regional government or the state government to drain the region. And but the early efforts to reclaim the flooded land was largely ineffective. And so there were a lot of floods in the 40s and 50s, big floods, which basically inundated the entire state for months at a time. So there was a federal project called CNSF project for flood control and other purposes that was designed, built, and constructed in 50s and 60s. So, and that project itself is what you see. Some of the highlights of that project covers an area of 18,000 square miles, pretty much from Orlando, where Disney World is, all the way to Florida Keys. We have about 8 million people growing every day and a very large ecosystem, the Florida Everglades or Greater Everglades ecosystem, 3 million plus acres of agriculture. And we have several water management districts, and we are the largest, and our mission is primarily flood control, water supply, water quality, and ecosystem restoration. We are one of the most complex water management systems in the world, perhaps. 2,700 miles of canals and levees, very large number of water control structures, and 70 plus water pumping stations. So none of the new issues like climate change or sea level rise were not considered in its design, and that's why we are facing some challenges today. So when you look at this particular graphic, on the left-hand side, you see basically a rendition of what the system looked like, what they call a river of grass, basically a very broad, large wetland very slow moving because the topography is very flat. Much of the area was much of the area consisted of sawgrass plains and region sloughs, and then the southern part more like what is now the Everglades National Park. So on the right hand side is what actually ended up with. You have the Lake Okeechobee agricultural area, and then what are known as water conservation areas, and then the Everglades National Park. And to the coast, you have a heavily urbanized area where you find Miami, Fort Lauderdale, and West Palm Beach. And so the system looks very different today with those changes. You see the agricultural pictures and then urbanization right up to the Everglades, which is creating a lot of issues of water management. And then what is left of the Everglades? Only about half of the Everglades is left today. So pretty soon, right after the project was constructed, then people realized there was a lot of environmental damage to the Everglades. There's too little water for the Everglades. The water quality degraded significantly because of the nutrients coming from agricultural areas and others. Water shortage due to droughts because of drainage or wet season. You need to get rid of a lot of water, and that creates sometimes droughts in the dry season. And then saltwater intrusion along the coast. A lot of water being discharged or lost to tide to provide for drainage. So significant loss of Everglades habitat. So pretty soon there was a lot of discussions about restoring the ecosystem itself, and that required sort of like multiple stakeholders getting together and having a discussion about what the restoration would look like. And I'll talk about some of these projects that you see on this graphic. It starts all the way from Kissimmee River Restoration project, which is the project I came to work on. Most of the projects that we have in place are some of the largest restoration projects in the world, like Kissimmee River is the largest river restoration project. We have stormwater treatment areas, about 50,000 of acres of constructed wetlands, basically dismantling what was constructed in some places. So as engineers or others, you may learn how to build things in school, but we don't learn how to undo things in school. And so this was a challenging effort. Now, in this restoration planning, we actually did not account for potential climate change or even sea level rise. So the question is, are these plans, which may cost billions of dollars, are they resilient or robust enough to, in the face of environmental change, climate change, or sea level rise? So that's the big issue. And then on the coastline, we got this other issue of sea level rise. You can see these tide gauges all around South Florida showing about 9 to 10 inches per 100 years. And that's a lot in South Florida. We have only 10 feet of elevation drop from Lake Okeechobee to the Florida Keys. So very flat area, and that's creating a significant challenges in water management. And lately, there have been some other discussion about the last 10 years or 8 years or so. There's a lot of discussions about that this region is becoming what is known as a hot spot over the U.S. The rate of rise in sea level has increased significantly during that 8 to 10 year period, and we see this in our coastal water control structures as well. And the question is this an episodic event or is that a persistent change? And which is kind of a bad news. If the rate has increased significantly, you see rates like 22 millimeters per year. When in general, we have had rates like 2 to 3 millimeters per year. So that's a significant concern of during the recent period. So we identified we have several challenges for our water management mission. Rising sea level is obviously the first one, then increasing temperature, change in rainfall patterns and the change in frequency and strength of hurricanes. And you see this little cartoon in the middle showing the challenges of water management. We have tidal storm surge, which will be exacerbated due to sea level rise, saltwater intrusion, and you see a little rock rotating down in the middle, which is basically like Swiss cheese. You can't build levees and stop this water coming through the groundwater aquifers. And basically, a lot of well fields along the coastline because that's where the development happened, and that's contaminating some well fields. And then on the lower left, you will see the southern part of the Everglades National Park or natural system, basically rising sea level and the effect of basically chlorides and sulfate causing peat collapse and changing the landscape there itself. And this little video you see is the one that I took when I was driving through Miami Beach, what we call sunny day flooding, clear skies, but water coming through the storm sewer system into the streets. And I heard stories like some people don't want to buy Ferraris anymore in Miami Beach because of the salt water coming into streets. So this is kind of the current system. We are seeing the impacts already. And then lately, we've been seeing what we call king tide flooding all along South Florida coastline. Everywhere around October, you have 2 or 3 days of twice a day flooding of streets and causing significant inconvenience to population. This is kind of a nice picture showing this person's house is normally dry during king tides. The water is coming through the storm drains back into his front yard. So this is kind of an ongoing thing, what we call a nuisance flooding, which eventually will become chronic flooding. So as a part of the flood control project, at the end of major canals discharging into the ocean, the project included some water control structures. They're called salinity barriers. Basically, the idea is that they will prevent saltwater intrusion along open channels, but at the same time, they will have gates to relieve rainwater from the interior areas like Miami. Now, these were not designed for sea level rise, or did not account for sea level rise. So twice a day now we have situations where we cannot open the gates because the ocean side is higher than the land side. And you see a picture inset in there that we have constructed some what we call forward pumps. When the gravity structure cannot be operated, we open those. Start the pumps to pump our water. And I feel like communicating these issues to the general population is very important. So we created this animation to demonstrate to people what happened with the system in this area, particularly with the sea level rise. These control structures, we cannot, open the gates because of the higher sea level during king tides, and when it rains, the interior areas could be flooded. So this is an important communication tool to communicate to the general public. And the issue of saltwater intrusion, for example, showing people that their well fields could be compromised, and the importance of things like restoration. So the other big issue is, because we have very porous geology, the water basically seeps through very easily through limestone aquifer. And as the sea level is rising, the water table also rises along with that. And you can see that the soil storage that is available to absorb the rainwater is going to be gone in the future, and you'll have more and more runoff coming into our canal system that needs to be discharged through those structures. So I call that like three whammies. You have three saltwater, sea level rise and storm surge. Then the water table is rising, and then if the rainfall intensities change in the future due to climate change, you get heat from all three sides. So basically, problem becomes very challenging. So this is showing that particular rock sample that I showed you earlier. you have a lot of well fields on the left-hand side. You can see right close to that red line, which is the saltwater intrusion line. And so the question is, in the future, how fast that saltwater front would move towards those well fields, and what do we do about it in terms of adaptation? So that acceleration of saltwater intrusion is a significant concern. So we do use climate hydrology models. South Florida modeling is very different from elsewhere in the country. That I learned actually pretty soon after I came here. We have a very complex surface water groundwater model where we use a two-dimensional grid for modeling surface water groundwater. But this model also has all the operating rules and management features of the system itself. So we do have good tools to look at impacts of changing rainfalls or changing boundary condition due to sea level rise and others. So in our planning, we actually did some modeling, but we use historical information from 1965 to about 2005 or 2012. And obviously, when you plan for a 50-year project or more, you need to consider the potential changes in your boundary conditions or drivers like rainfall, Europa Transpiration, and others. So this is why this particular paper you may have seen, stationarity is dead, and how do we do water management now? So we need a new paradigm. And so we started looking at this issue of how do we do planning in the presence of climate change and sea level rise, and we started looking at climate model information. So that's where I'm going to show you some of the work we had done to understand the climate projections and their skills in terms of potentially or for possible use in future planning. So what you have here is like there are several types of uncertainties in these projections. You have natural variability, but then you have model uncertainty and spread. If you work with climate models, there are like 20, 30 different general circulation models. And then you have those downscaled information. And in our case, we also have sea level rise uncertainty or ice sheet uncertainty. And so all those things actually will add to the model uncertainty and spread. Then you also have scenario uncertainty due to future greenhouse gas scenarios. So the question for us, the engineers and planners, would be, what are the climate change implications in water resource investigation? Do you use scenario-based approach, or do you use all models, or you use what is known as model culling? Basically, throw out the models that are not skillful, but keep the ones that seem to work very well in your region. So this is kind of where we started. So in terms of natural variability, we have very good signal in terms of teleconnections, like El Nino, La Nina. We have in the dry season, very good signal. But we also seem to have a multi-decadal signal in terms of tropical storm frequencies and patterns. And then we also see a multi-decadal patterns of rainfall. And they seem to be related to the Atlantic multi-decadal oscillation, which is through a teleconnection. So these types of multi-decadal natural variabilities are kind of a nightmare for planning because they don't have fixed periodicity, and so that's a big issue as well. And what our inflows to Lake Okeechobee, which is our major water supply source, is significantly impacted by those decadal variabilities, as you can see on the graphic on the lower left. So that's the natural variability. So we kind of followed the sort of the California example. We kind of use a fairly logical approach, in my opinion, to look at this problem of climate change information. We first look at the observed climate data to see if there is any evidence of climate change in Florida during the historical period. Then we look at the general circulation models. We have looked at this couple modeling intercomparison project model suites, CMIP 3 and CMIP 5. Then we looked at the 20th century model output to compare those with the historical data to see do they have any skills in Florida. Then only we will use 21st century data for for projections. Obviously, the global models are very coarse in resolution, as you will see in a minute. So we have looked at the downscale data. And then finally, we also want to look at do these models represent those teleconnections very well? And then we will use that for planning purposes. So you can see this graphic, and probably some of you are familiar with the global models and their weaknesses in terms of resolution. Florida being an unusual location with ocean all around, there's quite a significant effect of the oceans on the rainfall patterns and climate within the state itself. You can see some of this model, half of Florida is underwater if you go with the GCM resolution. So that itself is a big issue. And when you look at the model data itself, the rainfall pattern doesn't even compare well with respect to seasonality. You can see on the right hand side the temperature seasonality is fairly well, and these models have significant biases that we have found. And so clearly you need some sort of a bias correction for us to use before we use those in planning. And so we started looking at the downscale information. We've looked at the Bureau of Reclamation's bias-corrected spatially downscale data or constructed analog data. We've also recently looked at through a project through FIU and Penn State self-organizing maps approach for creating downscale rainfall information. And the latest and apparently the greatest, the LOCA data set, we are also looking at that. We also looked at the dynamically downscale data from NARCAP, from NCA in Boulder, and we have we're looking at some of the other dynamical downscale data as well. So what we are seeing is, you can see for the CMIP 3 on the top figures and the bottom figure CMIP 5, and each figure has a percent change in rainfall or precipitation on the horizontal axis and the absolute change in temperature on the vertical axis to get a general idea of what kind of a change we could expect. And we saw that CMIP 3 and CMIP 5 kind of showed gave two different set of answers for precipitation, but for temperature they were fairly consistent for the what we call a near future, that is 2050s or so, or far future, more like towards the end of the century. We also wanted to know if there's going to be a seasonal changes, and what we are seeing in this model downscale data set is that the summer rainfall is going to be decreasing, but the early dry season of September, October, November period, we're going to have higher rainfall. So this seasonal change, if it is real, it's very important for water management. So we need to think about that, and I've worked on that already. We also see a very definite spatial pattern in percent change in temperature and rainfall across the state, and each graphic showing from south to north the temperature changes, temperature increase becoming more and more increasing as you go through to the northern latitudes in the state for both CMIP 3 and CMIP 5. When it comes to rainfall, you see a decrease about minus 10% in CMIP 3 but actually positive increase in CMIP 5. And that's where I said you get two different sets of answers for those. Different models have very different spatial patterns. And one of the other things we saw was also the evapotranspiration is important. And we've looked at the climate model data to look at, can these models be used to predict evapotranspiration? And what we found out was that because these climate models don't represent the summertime cloud cover very well, the ET actually is overestimated in the summertime because they don't have the cloud cover represented very well. And that obviously could be very significant to your impact assessment for water resources planning. So that was another challenge. We also wanted to look at the extremes. We looked at for the bias-corrected data, the extreme rainfall, And probably this is fairly well known. This climate model, the downscale data are very poor in representing extremes, and we saw biases up to like 50 to 60% in extreme rainfall. So there's a lot to be done in those in these climate models with respect to extremes, in my opinion, before we can use them. In any case, to get the ecologists involved, we actually came up with some scenarios and ran through our models to see what kind of changes we might see. So we needed to come up with some scenarios. We used early on a Bayesian approach. I think that was published by Tebaldi and others. I won't go through the math or details on this. And the idea is like the criteria is which models have the least bias and which models basically give the same type of results through what is known as convergence. And based on that, we actually came up with some scenarios for future 1.5 degrees centigrade into the next 50 years, and plus or minus 10% rainfall change as a scenario for future impact assessment. So based on those numbers, we came up with those scenarios, 1.5 degrees plus or minus 10%. We also incorporated sea level rise of 1.5 feet. I'll talk about that in a minute. So we actually have modeling scenarios. We came up with 7 modeling scenarios. For example, 10% decrease in rainfall, 10% increase in rainfall, temperature increase, which will impact the Europa Transformation. So we came up with 7 scenarios to look at. We actually ran the model, and we saw significant impact on the Everglades in a case of temperature, 10% decrease in rainfall and increase in Europa Transformation. And you see the coastal area is blue. That means there's an increase in water table due to sea level rise. So these are very good scenarios for us to assess ecologically what could happen to the Everglades in these types of scenarios. And that was given to the ecologists. There's a series of papers published on that if somebody's interested. So we'll also look at the global, regional, and local sea level rise projections. And this is one of the topics I've been involved at the national level, particularly one of the DOD studies and also NOAA studies. So when you look at global sea level, you have thermal expansion and ice melt, which is where the biggest uncertainty is. And then regionally, you also need to look at the vertical land movement, the ocean dynamics changes, and the gravitational effects. Basically, as the ice sheets discharge their ice into the ocean, the gravitational field across the globe changes. So you need to account for that. If anybody is interested, there are a couple of reports on that published by Department of Defense and also NOAA in 2017, where all those components were accounted for and provided regional sea level rise projections. In South Florida, there's a lot of discussion about sea level rise. Fortunately, the 4 counties in the region got together, which is very unusual, and assembled a scientific, ad hoc scientific group which came up with what we call a unified sea level rise projection. So all the counties, municipalities, and regional governments are using the same set of projections. That ensures consistency across the area. We also needed sea level extremes for our flood protection planning. Basically, the idea is with sea level rise, how do we predict storm surge and peak water levels along the coastline? So we currently use what is known as an empirical simulation technique. Basically, it involves deep-hiding the data, using the non-tidal component analysis, wavelet analysis to simulate storm surge, and extreme value distribution fitting for the extremes, and then doing a large number of Monte Carlo simulations to develop frequency curves for storm surge under sea level rise scenarios. So in terms of adaptation, there is a lot going on in the state, and these are a little graphic showing different things that are being attempted. You see the Everglades restoration, we think, is one of the best restoration adaptation strategies. It will provide more water to the Everglades, possibly slowing down the peat collapse that you might see in the future and providing more water to the urban areas. We think water conservation is one of the best, what we call a no-regret strategy. And fortunately, the counties have already reduced the water consumption significantly. Additional water storage, levees and pumps are going to be probably needed in some places. Relocation of water supply well fields, green infrastructure, and probably interior empowerments to store temporarily until the tides subside. So these are the different things that are being tried or considered in South Florida. So let me talk about this decision making and the deep uncertainty, which is an area that we are getting into. As you all probably know, there's a lot of uncertainty in climate models. There's a significant uncertainty in sea level rise projections, and decision makers don't have a good idea how to make decisions in this type of setting. And this is known as deep uncertainty, probably pioneered by Rand Corporation and others. And the idea is typically in planning, we use what we call predict and act scenario, but in this case, we are doing more like explore and adapt approach. Basically, you see a method that Rand Corporation is using. So we're considering three approaches: robust decision making. Rand has a project in South Florida. We're also considering decision scaling or bottom-up approach that Casey Brown and others have developed. And then lately, we're working closely with the Dutch Delta RS in the Netherlands on what is known as dynamic adaptive policy pathways, basically sort of like an adaptive management approach. And I'll kind of mention some of those real quickly. For one of the coastal areas where we are trying to provide some adaptation strategies for flood protection, so we have a hydrodynamic model. Basically, we have drivers of storm surge and rainfall. And then we also have an economic damage model called FIAT that the Dutch have developed. And then we are looking at adaptation options. So the first one will be local mitigation strategies, flood walls and pumps. Then we also have regional flood mitigation strategies, in our large-scale system, some forward pumping. And eventually, the other option has to be the land use mitigation, basically elevating buildings and roads. So which combination works for this system and when? So the idea is you see on the bottom graphic expected annual damage versus sea level rise magnitude for different adaptation strategies. And eventually you come up with what is known as a dynamic adaptive policy pathway. You start with one set of scenarios and switch over to another when the sea level rise reaches that tipping point. This seems to be a very useful approach to deal with uncertainty and perhaps more palatable to decision makers. So you're not going to spend a lot of money up front, but at the same time, you need to make sure that you're not preempted from adapting another solution later. So I think it's a very logical way to look at that. The RAND approach of what is known as robust decision making, basically the four levers, the uncertainties, the XLRM approach, levers, and then models and metrics. And that was used in Broward County as well, and they came up with this type of graphics, basically evaluating the risk for different drivers of sea level rise and precipitation, and how the values of the assets change and the change in hazards due to sea level rise and precipitation. So let me I think I have about 5-10 minutes. I went quickly, but I want to leave some time for questions. I want to talk about this hydrologic design and the nonstationarity. The work I've done with my my colleague and former advisor, actually, Professor Pepe Salas from Colorado State, and few others, and we've been working on this for some time. So the whole idea is, if you take the sea level rise or even floods, you're trying to design a project for the future. And then basically the idea is your probability distribution is changing with time, your extreme value distribution, you're trying to come up with a design quantile or design flood or design water level that is valid for, let's say, 50 years into the future, but your probabilities are non-stationary. And your exceedance probabilities keep changing with time. So this is the scenario very different from the stationary scenario that we have taught in schools. And in this scenario, there is no such thing as a fixed return period, because return period itself is changing with time. So the question is, what is the new paradigm for hydrologic design? The other aspect is that the frequency of flooding will also increase in the future. If you design for a particular flood or level, your frequency, initially will be more like nuisance flooding and will become more chronic flooding. So we have worked on a method that could incorporate that frequency of flooding as a criteria for design. So there have been several methods for this type of design, traditional return period approach, but basically modified for non-stationary condition. Risk-based approach called DLL or design life level, or use the number of events as a criteria for design. And this paper you see on the lower left-hand side was basically published very recently. That is useful to look at this type of approach. So these are some of the results. Basically, the idea is like, this type of return period curve shows in order to have, let's say, if you design for 50-year return period, what is the actual expected waiting time or return period over the non-stationary period? In this case, it's more like 22 years. So you can use this curve in reverse and say, if I need a 30-year level of protection, it tells you really need to design it for 90-year return period today. So this paper was published a few years ago, actually received several medals for it because this is a new paradigm for design. And it tells you also how the risk changes due to non-stationarity, and that is also very useful for design as well. So if you're interested, there's a whole bunch of papers here talking about non-stationarity, and there's a task committee in EWRI of the American Society of Civil Engineers that I chair, and a couple of my colleagues are chairing, that we are trying to promote these concepts for hydrologic design. With that, I also want to mention there's a lot of media interest in Florida. Even Rolling Stone was here and wrote an article called Miami is doomed or something like that, and that didn't go very well. But National Geographic and others. So there's a lot of interest in South Florida because it's a hot spot for sea level rise and in some cases climate change. And with this, my favorite closing slide, I will stop here. I think, Sarah, we have plenty of time for questions and discussion, I think.
Certainly. Oh, that was wonderful. I'm a big fan of pictures, and this is a great way to put a smile on everyone's face for today. So yes, please feel free to enter questions into the chat queue. We do have one that is from Andre Dozier, who's part of our group here at CSU. He has a question about best management practices, and in the decision scaling technique you've written about, how many of those practices have actually been implemented already?
So the one that, this is something new for us. I'm going to kind of go back to this one. So we started doing this recently. I mean, the studies have been done, but the idea is these studies will provide guidance to the local management to prioritize these adaptation options. So we think that studies like this one, for example, where we use the dynamic adaptive policy pathways, will be a guide for them to implement, adaptation options. For example, many places they're already building pumps, like Miami Beach. They're spending $400 million for, or maybe more, for building seawalls and pumps for that nuisance flooding you saw. So they are being implemented, but I think these types of analysis, which are sort of new, will provide those types of decision-making guidance for them to implement projects. So, but in the other countries like the Netherlands, they have already implemented some of these approaches in practice. So the short answer is they're just beginning to be used, and it's too short a time frame where we got into this decision scaling or dynamic adaptive policy pathways in practice. And I think this is where it's, and the incorporation of economics will be the future for resilience and adaptation.
Great, thank you. I'm going to try and turn on Doug's microphone. Doug Yoder, I'm going to give this a try. If it doesn't work, no worries. Can you give it a try, Doug?
I can give it a try. Can you hear me?
Okay, loud and clear.
Hi, Doug.
Hi, Obi.
Yeah.
Well, you knew I would have a question for you.
I know. I didn't ask you. Remember, I didn't ask you a question when you presented, but it's okay. I'm very happy to have a question.
Oh, well, you see, you left too much time. Have you looked at kind of the going from the other direction, which would be how much forward pumping capacity could you realistically apply to the regional system, and how would that pumping capacity then maybe relate to some amount of sea level rise?
Yes, we have. So we have done some in-house analysis to see we had the gravity structures along the coastline, and they had a design capacity, dates back to 30 or 40 years, right? So we have a curve that shows with the sea level rise how that capacity is decreasing with time, right? Because of the sea level rise. So we know how much capacity we need to add to forward pump with forward pumping to regain that lost capacity due to sea level rise. So the question is, do we want to get back to the original design capacity? And that's where we are looking at what is the level of service that people would like to have. Is that the level of service they had in 1950s, or is there a new discussion on level of service we need to have? Because the land use changes have changed the level of service already without the sea level rise. So I think that discussion is happening, but we do know that pumping capacity required to get back to that original design capacity as a function of sea level rise. And as you know, it is not a simple thing to put forward pumping. There are a lot of other complications. There's no land. These are very expensive, and a lot of so it might be a mixture of things. Like in Miami-Dade, we have Western impoundment with the forward pumping in combination. So you pump into the Western impoundment temporarily, and then let water out after the tide subsides. So there has to be a combination, but the level of service program which we just started, hopefully we'll look at all those mixture of things. But does that probably not the answer you're looking for, but at least we are beginning to look at, Doug.
Well, no, I was just trying to determine when my house is going to flood. That's all.
Yeah.
We'll know that soon enough.
I'll make sure that get addressed in the study.
Great. So we have another question from Jessica Bolsa, and I'm going to try and turn her mic on. She's in your neck of the woods.
Yeah, I know Jessica. Hi, Jessica.
Yeah, hi, Obi. How are you?
Fine. How are you?
Good, thanks. So that was really interesting. So I was finding myself thinking about, how I guess the higher up elected officials and decision makers receive these models of non-stationarity and risk. And I was wondering if you could just talk a little bit about, your experience communicating about uncertainty and some of the approaches that you're describing with the decision makers.
Yeah. So fortunately, we last month at the governing board, there was a presentation on sea level rise. So I think the governing board members or decision makers showed a lot of interest and were excited that we are addressing sea level rise. I won't get into the politics of it. I will stick to the science aspects of it. But I think there's a lot of interest. But I think, like I mentioned earlier, this decision making under uncertainty or deep uncertainty is not something they're used to. So I feel like we as analysts or scientists or engineers, we need to give them tools that will allow them to come up with decisions, using things like DAP or dynamic adaptive policy pathways, that they feel comfortable and they feel that we have addressed the uncertainty adequately. So I think there's some homework we need to do before, and before we ask them to make decisions. But I feel comfortable we will have enough tools to educate them how to make decisions. And so I think we'll have to wait for some time. But places like Miami Beach, as you know, they had to make those decisions, and they convinced the citizens to spend the money because their chronic, flooding was sort of chronic, and their risk tolerance was less and less as the time went. So we need to work on it, and I hope the decision makers will give us enough resources to work on these solutions and methods. I don't know if that was the answer you're looking for, but it's probably, without getting into politics, that's probably the best I could do.
Yeah, no, that was very helpful. Thank you.
Okay, great. So Harry Zhang has a question. He's from WENRF. I'm going to see if we can turn your mic on, Harry. You might have to unmute your phone.
Okay. So this Harry.
We got you.
Okay. So for this modeling, I think I see you for the flood modeling you use XP Swim. I know there's also other versions swimming around. I'm just curious whether there's a particular reason you want to use this XP Swim, or you just pick one, I guess. That's all.
No, there was a particular reason. I tell you, as a modeler myself, I'm now very happy there is no single tool that will model this system well. As I mentioned, we have very high transmissivity. Geology is very different. The surface water groundwater interaction very strong. Then we have very complex water management. Area is very flat. So you really don't have in my opinion, a single tool that models the urban system in Miami-Dade County very well. And that's an area of research, I think. But I could tell you why XPSwim was picked, because that was the model that the county had used. And this initial study, we thought, okay, let's not try to reinvent the wheel. We'll use that because there's a starting point there. But we soon realized the weaknesses of those models. So we have tried the Army Corps of Engineers RAS models. We have tried to combine MATRO model with RAS models. We are trying to use the Flow 2D model and RAS 2D. But again, because of the complex surface water groundwater interaction and complex water management operation, really need to do some work to find or develop a good tool. So it's just we had the opportunity to use XPSwim, and going forward we might not. I know county is moving forward. We'll have to wait and see how it does in the future.
Thank you.
Yeah.
Okay, and we have one final question from Chip. He is wondering what forward pumping is exactly. He's not familiar with that.
Yeah. So typically, you have a flooded area, you put a pump station, pump back into, let's say, Lake Okeechobee or some storage area. So basically, forward pumping is you have a gravity structure, let's say from a city of Miami, you pump into the ocean, or you let the water out into the ocean through the gravity structure. Now, when the gravity structure is not functioning due to sea level rise, you need to pump out the water, and that we call forward pumping. In other words, in the same direction as the gravity flow was, you enable have the pump to pump out water in the same direction. So that's a standard term we use. It's probably not around here, but it's probably not the globally used wording. It's the same as pumping, but in the same direction as the gravity structure was. But when the gravity structure cannot function due to higher sea level rise, you basically pump out water in the same direction. I don't know if that explains it. That's kind of what it is. Nothing fancy about it.
Great, thanks. He says that makes sense. So, well,
Yeah.
that was the last question I saw. Do you have any concluding remarks, Obi?
No, I think that I feel like this area is an opportunity for a lot of people to do a lot of things, and I feel like this issue of rainfall extremes is a big one. I think we don't know in a regional sense how the extreme rainfall might change and how the intensity, duration, frequency characteristics might change. And a lot of people blindly use these climate models. I, for one, believe that there's a lot more work that needs to be done for rainfall extremes. This whole issue of compound flooding due to storm surge, water table rise, and rainfall, that's an area of research that needs to be conducted. And this whole idea of decision making under uncertainty and I think in this kind of setting for adaptation, that's another area of research. So there's a lot of open topics to be looked at in this region. So if anybody wants to come down and work on it, please contact us.
Great. Well, thank you so much for your time this afternoon, everybody. As mentioned, we're ironing out the details for our next round of presentations, and I'll be sure to send out that information once we have it finalized, as well as a link to this recording so you can forward it along to anyone that wasn't able to participate today. Hope you all have a wonderful afternoon and a great weekend. Take care now.
Thank you.